Today's lesson, 8.4, is on angles of elevation and depression, and it follows up on lesson 8.3 from last class where we talked about how to find the missing side of a right triangle using trigonometry. And so today what we're going to do is we're going to define what the angles of elevation and depression are, and we're going to use the angles of elevation and depression to solve some word problems. And then during class, we're going to have an activity of measuring the height of Garin Hall, but I'm not going to talk about that right now during this presentation. All right, so by the end of class, you will be able to use trigonometry ratios to solve word problems. That's our objective for the day. First, let's talk about what angles of elevation and depression are. So suppose a person on the ground sees a hang glider at 38-degree angle above the horizon line. So here's a picture of that, and you can see compared to the horizon line there, this little girl is looking up at the person in the hang glider and is looking up at a 38-degree angle. This is the angle of elevation. She's looking up to see it. Okay? But at the same time, the person in the hang glider sees the person on the ground at a 38-degree angle below the horizon line. So there's the horizon line, and you can see that they're looking down at that little girl at a 38-degree, and that is called the angle of depression because he's looking down. And notice that these two angles are congruent because they're alternate interior angles. So both of them are 38 degrees, they are congruent angles, and you can use the angles of depression or elevation as the acute angle of a right triangle formed by the horizontal distance and the vertical. So I can use them as a right triangle and then use my trigonometry to find the sides of that triangle. All right, so in our notes, the angle of elevation is the angle created with the horizontal when one looks up at an object, as opposed to the angle of depression is the angle created with the horizontal when one looks down at an object. And here's an example. You can see there's a person in the balloon and looking at a tree, and someone lying down the tree looking up at the balloon. And again, the horizontal lines are parallel, and the angle of depression and the angle of elevation are going to be equal in that case because they are alternate interior angles. Here's a different example of a person looking up at an airplane, so that's the angle of elevation, and looking down at a dog at the bottom of the hill, that's the angle of depression. Those are obviously not alternate interior angles, so those are not necessarily have to be equal. All right, so here's a quick example problem for you to determine whether these things are angles of depression or angles of elevation. So looking at that first one, that is someone in a plane looking down at a person in a balloon. So that would be an angle of depression. Number two is that person in the balloon looking up at the person in the airplane. So that would be an angle of elevation. Number three is the person in the balloon looking down at the base of the mountain. So that would be angle of depression, looking down. And then number four is an angle of elevation because it is a person at the base of the mountain looking up at the person in the balloon. All right, looking at B, number one is an angle of depression. It's a person in the plane looking down at the person on that cliff. Angle 2 is the exact opposite. It is the angle of elevation. It is the person on the cliff looking up to see the cockpit of the airplane. That same person in number 3 is using an angle of depression to look down at the sailboat. And in number 4, someone in the sailboat is looking up to see that person on the cliff. So that is an angle of elevation. All right, let's do some example word problems. Imagine a 10-meter wire is attached to a pole that reaches a stake in the ground and makes an angle of 51 degrees with the ground. Well, let's draw that. Here's a right triangle. I've got a pole. There's the ground. There's the wire. And again, it's a right triangle. And we know it is a 10-meter wire. And it makes a 51-degree angle with the ground. All right, now it says find out how far the stake is from the foot of the pole in meters. So that would be right here. That's how far the foot of the pole to the stake is. Okay, and then round your answer to the nearest tenth of a meter. All right, so we can do that. So first of all, like I always do for trigonometry problems, I'm going to write down SOHCAHTOA and determine which sides in this triangle I have to help me determine which ratio. So when I look at this, I have my hypotenuse, my opposite, and my adjacent. And I have the hypotenuse. I know that the wire is 10 meters long, and I will have the ground, it's x. I'm going to use that to find out how big the ground is. I don't know anything about the pole, nor do I need to. So if I have A and H, then using SOHCAHTOA, I'm going to have CA, or I'm going to use cosine. So the cosine of 51 degrees, that angle there, is equal, like all cosines, to my adjacent over my hypotenuse, which in this case equals x over 10. So there's my equation. If I multiply both sides by 10, the 10 on the right cancels, and I'm left with just x. And on the left, I have 10 times the cosine of 51, which is equal to about 6.29. But the problem asked me to round the nearest tenth of a meter, so the answer is going to be 6.3 meters. Let's do another problem, example problem number 3. A person is flying in a balloon and looks down to the landing spot on the ground. So we can draw that. There's the balloon, there's the landing spot. The line of sight makes a 21-degree angle with the ground. So there's the line of sight, and it makes a 21-degree angle with the ground. If the balloon is 525 meters high, so there is a right angle because the balloon makes a right angle with the ground, and the balloon height we said is 525 meters. Find out how far in ground distance. Well, the ground distance is right there, the distance from the balloon to, or the distance from the point on the ground under the balloon to the landing spot, and we need to find that distance, so we'll call that x. We need to find out how big that is, and now we need to round our answer to the nearest tenth of a meter. So, like all problems with trigonometry, I'm going to write down SOHCAHTOA and put on the sides that I have. I know I have the hypotenuse, I have the opposite, and I have the adjacent. So now I'm going to look and see which of these sides I need to solve my problem. Well, I have the balloon height is 525 for my opposite, and I'm trying to find the ground distance x, which is my adjacent. And so I look at my ratios, which one has, in SOHCAHTOA, which one has O and A, that would be TOA, the T of which stands for tangent. And so I know the tangent of my 21-degree angle, like all tangents, is going to be equal to my opposite over my adjacent, which in this case equals 525 over x. So I know the tangent of 21 equals 525 over x. Multiply both sides by x, and those x's cancel. So I know that x times tangent of 21 equals 525. Divide both sides by tangent of 21, and the tangent of 21's cancel, so I know x equals 525 over the tangent of 21, which is equal to about equal to 1367.67, but the question is asking us to round to the nearest tenth, so that would be 1367.7. Right, now that we've gone through some example problems, you guys can try some problems like this in your classwork 8.4, Trigonometry Word Problems.